First of all, this is a video to explain the internal flow case 1, where you have a constant surface temperature and a fluids flowing inside the pipe. So a few days ago, we already used this diagram to discuss the temperature change for the fluids inside the pipe. At the beginning, the cold fluids enters a hot pipe. But however, at the beginning, the temperature of the fluids almost entirely is the same as the cold temperature. Only the very, very edge on the surface of the pipe will be changed slightly. But as it flows through the pipe, the heat will be transferred from the pipe to the fluids, and then the temperature will gradually increase till the end. And of course, if your pipe is really, really long, then in theory, we can imagine the fluid can increase to the same temperature of the pipe. And then, of course, within the diameter or the radius of the pipe, the temperature of the fluids is also different because the center of the pipe will be slightly colder than the edge or the surface of the pipe. That is because of the heat transfer needs to transfer from the center to the edge or from the edge to the center. So there is a temperature profile from the center of the pipe, the blue color at the beginning, to the surface of the pipe, the red color at the beginning. But anyway, so this has been discussed. And then here we also use this type of diagram to analyze the energy balance for the temperature change of the fluids. Okay, so because the temperature is different from the center to the edge, so therefore we have a mean temperature. So if for the first spot we have mean temperature 1, and the mean temperature 2, and the mean temperature 3, etc. And then today, however, we will use a thin slice, using this thin slice as the object of analysis and construct the energy balance. So if I define the left side of the thin slice is the position x, and then the right side, the position would be x plus delta x. And then the surface area where the heat can be transferred from the pipe to the fluids are actually basically the perimeter of this thin slice. So if I draw a diagram of this thin slice, would be something like a very, very thin disk. And then the heat transfer will be through the edge surface area of this thin disk. And then, of course, the left side is x and the right side of delta x. And you can calculate the volume of this fluids, and you can calculate the thermal capacity, and then also calculate how much heat you need to in order to increase the thermal energy or the internal energy of this volume of the fluids. So the energy balance will be still same as before. So the change of the internal energy, or you can use U in thermodynamics, or now I just use E stands for that. So if I say stored internal energy in the volume, that would equals to how much energy that flows into this volume, and then how much energy it flows out or leaves this volume. Remember, there is fluids coming from here, there is fluids coming from here. So these fluids carry their own thermal energy. That's the inflow and outflow of the energies. And then in theory, if you have a generation of energy inside this volume, then you would have this generation of energy. And then in addition to that, then you would have the amount of the heat and then amount of the work. And of course, I use plus here. So the heat is defined as transferred into this volume, and the work is also defined as done onto this volume. This is a liquid, so the volume change is negligible. there's no work. And then there's no chemical reactions happening inside this volume. So there's no heat generation, energy generation here. So the equation is simplified like this. And then in addition to the this energy balance equation, we take the rate of everything instead of the total amount of the energy. So the rate of the change of the energy, the change of the influx and outflux, and the change of the heat, that is a heat transfer. So this is basically the amount of the lowercase q. That's the heat rate, the rate of the heat. And then at steady state, the change of the internal energy equals to 0. That's because it's at a steady state. So the energy that the material carries in, that equals to the mass flow rate times the heat capacitance, the specific heat, and then times the temperature. And then here, however, I just want to remind everyone, this is the first time we use the mean temperature because remember, the temperature is different from the center to the edge. So if we talk about the temperature at this position X, we use the mean temperature at this position X, okay? And then this is at X, and then minus the energy that carries away. So it will be the mass flow rate, specific heat, the same thing. And then, however, the temperature on the right side will be the temperature, the mean temperature of X plus delta X. That is these two items, and we don't have generation energy, we don't have work. So therefore, the last one we have Q. The Q is taking the derivative dot on top, so that is the lowercase q. And then by definition, that is equals to the convection coefficient multiplied by the surface area. The surface area is the basically the edge surface area of the disk. That will be the perimeter. That's 2 pi r. R is the pipe of the radius of the pipe, and then multiplied by the length of the disk or the height of the disk is delta x. This is basically the surface area of the heat transfer. And then by definition, it is the delta T between the surface and the fluids. And here, again, by fluids, we have to use the mean temperature, okay? All right, so here we can rewrite it. That equals to M Cp. And then I'm gonna make sure that the second T minus the first T, the T at X plus delta X minus the mean temperature at X. So I swap the order of these two items. So I have a minus sign here. Okay. And then the other one is H 2 pi R pipe, and then delta X, and then Ts minus T mean. Still the same, okay? So now you can see it is a derivative of the temperature differences. So I'm gonna just move this first item to the left side of the equation. So I'm gonna have Tm at X plus X, delta X, and then at X, okay? And then that I moved to the left side already, that equals to here, H 2 pi R. This is the perimeter of the pipe, okay? And then divided by mCp. That's moved from the left side of the equation. And then I have here is Ts minus Tmin. And then I have delta X. Delta X I moved to the left side. So you can see the left side of the equation now, actually by definition, it is a derivative, basically the definition of derivation. So this actually becomes T delta Tm over delta x, that equal to the right side of what it is. So if I replace this 2 pi r as the parameter, so that would be h parameter, mass flow rate, specific heat, and then I have Tm minus Ts. Because I swap the Ts and Tm in the parentheses, then I have a minus sign here. Right? This equals to I'm gonna do integral. The left side, I'm gonna integration, and then the right side, I'm gonna integration as well. The constant, I moved it out. And then the range of the integral is basically from the entrance to the exit. And then the entrance would be T, basically the mean temperature at the inlet. And then this will be the mean temperature at the outlet. And of course, on the right side, the range would be x equal to 0 at entrance. And then the upper bound will be x to the length of the pipe. And then you can do the integration yourself. The left side is a log scale. Right? So if Ts is greater than T mean or the fluid's temperature, then the delta T at the outlet will be Ts minus the T mean at the outlet. And then delta T at the inlet will be this. This is just to tell you the numerator and then the denominator can be positive at the same time or negative at the same time. And then if we have this case, then we would have a and then basically you can plot it as a function, the temperature at the outlet or at any position can be plotted or written as a exponential function with the length of the pipe. So of course, this is outlet and L, and otherwise, if this is a function, then this will be a function of the X. Okay, so if we plot it, then we'll see this is X, and then this is the delta T. At the beginning, it will be greater. That will be the surface temperature minus the inlet mean temperature. And then it will decay exponentially. If you have a really, really, really long pipe, X goes to infinite, then the delta T will go to 0, right? Because exponential decay. And then the way that I draw is I use the delta t as the y-axis. But if you don't use delta t, if you use t, then you would have to have a surface temperature, and then your inlet temperature. And then you can see as it goes by, your temperature would increase from the inlet temperature towards the surface temperature exponentially. And if you have a long pipe, then you will reach the surface temperature. Of course, the way that I draw right now, the surface temperature is higher than the inlet temperature. If it's opposite way, so for example, if you have a hotter water, and then you have a colder pipe, then you would have a opposite decay similar as well. So the temperature will drop exponentially towards the cold pipe temperature. All right. So this is the temperature profile along the position. Along the position, it follows the exponential decay position function. And then to go further, I'm gonna use this equation to rewrite it. Just a second. I'm gonna just rewrite it so I can have expression of this HPMC term for the calculation of the Q. So I'm going to rewrite it. M MCP, that is in the denominator of this right side. And I'm going to just move to the left side and then move everything to the right side. So that will be equals to minus HP and then the log. That is the capacity of the capacitance of the water, of the fluids. And now let's calculate how much overall the amount of the Q. Okay, so the Q would equals to the total amount of the heat that has been transferred into the fluids within the pipe. So basically, if you have a pipe, and then how much Q is transferred on the entire pipe or from the entire pipe, all right? So in order to do that, then we construct the energy balance of the fluids at the beginning and then fluids at the end. So the amount of the Q that has been transferred, that must be equal to the delta energy between the inlet and then the outlet. And then how much it is? It is the heat capacitance multiplied by the temperature change of the fluids, the outlet temperature minus the inlet temperature. Okay, so then I just continue to calculate this. The Q still equals to mCp. All right. Do only one thing here. I do a small trick. Minus Ts plus Ts. So I basically minus the surface temperature for every single of these temperature. So they cancel each other. If you look at here, it's negative sign, and then this is a positive sign. So they cancel each other of these two Ts. It doesn't change the mathematics. And then however, here, it is the delta T outlet. And then this is the delta T inlet, as you can see, right? So I can rewrite it. So equals to mCp minus T outlet plus the T inlet. All right. So from what we got here, what MC equals to, then I just put it here, MC equals to HPL log out, and then out. There's a minus sign here. So I forgot there's a minus sign here. And then that will be HPL. And then delta T out minus delta T in. Because there's a minus sign here, and that's why the order of the two delta T swapped. And then you have the reason why we write this total amount of the heat transfer in this way is because now we can see this is the H convection coefficient. And then this is actually, you can see the perimeter of the pipe multiplied by the entire length of the pipe. So this is the area of the pipe. So you can see we can rewrite it as H multiplied by the pipe and then multiplied by a combination of the delta T's. And then in this case, we call this one as a log mean temperature difference. So delta TLM. So it is log mean temperature difference. Temperature difference. So in this way, we can do this. HA multiplied by the Q. This is important because the temperature or the delta T is changing exponentially. The delta T is changing exponentially, or here exponentially or exponentially. So you cannot take the delta T at the beginning and at the end, you do a simple averaging. You cannot do this. You cannot average this and average this. What you can do is you take the log mean calculation to get the effective temperature difference for the heat transfer across the entire pipe. And in the past, in our chapter 2, we, by definition, Q convection coefficient multiplied by the surface area multiplied by the delta T. This is the early scenario when we have a single situation. And then, of course, if you calculate the local situation, that will be the case as well. But when you calculate the entire pipe for the internal flow, you have to use a log mean. And the log mean is by definition the difference at the outlet minus the difference in the outlet, and then divided by the log of the ratio of the two differences. All right, you're gonna use this again and again. Hopefully, you will be familiar with this.